out what the storms are going to do, say an hour from now, 6 hours, 12 hours, all the way up to 7 days. We're also getting information, lots of information from our radar, satellite, and observations. And then, of course, we're going to really focus on this part of it tonight and helping to complete that puzzle, because sometimes we don't have, there's gaps in the information. We don't have it all. And that puts some question marks into the forecaster. Our confidence level may not be as high as if we're not getting those reports from the field. And eventually, once that confidence grows enough, we're going to be putting out that warning through whether it will be no weather radio, through your local TV radio, outdoor sirens, and especially your phone. And so that's kind of the whole process that we kind of go through. But again, tonight we're going to concentrate on that ground truth portion. A couple of options when we send out the warnings, disseminations. We're not really much in the business of developing apps, but you can go to mobile.weather.gov for some real basic stuff. It does have some radar observations and forecasts. FEMA has a good app just to get those latest real-time alerts, whether it be tornado warnings, severe thunderstorm, blizzard warnings in the winter. Well, it'll all be there. Third-party apps. There's a lot out there. It really all depends on, say you want some maps for looking at radar and situational awareness. There's a lot out there, and it all really depends on how much you want to pay for. You know, there's nice apps for $3 or $4 a month, and then there's some that are free. And of course, then you just got to fight through all the advertising. All right, this map shows all those little green dots you see. It's all one of our individual volunteer SKYWARN spotter locations across northern Colorado. And right now, boy, we're over at least 10,000. But it's amazing how still storms can go in between all of our spotters, and then so we're still kind of wondering. So we can never have enough. You can certainly see where all the urban areas follow the highways. There's I-76 through there. Anyway, and then what we can do, we can overlay our radar on top of these. And so if it falls over, maybe this storm's going over your location, you may even get a call from us. So hopefully it's a two-way street where you can call us, we can call you, and kind of get that full picture. And after tonight, you guys too can have your own little green dot. That's why we ask for your addresses and your phone numbers, and we'll put you right there, and you can have your spot right here. All right, and since I've got a radio group tonight, amateur radio, I got a slide just for you guys. Normally, of course, this summer is a little bit different, but we do have a spot in our office for amateur radio folks for running the net control. And this picture here was taken during one of our recognition days. This was back in 2018. And so it's really cool because it allows some direct communication between you guys out in the field and our warning forecaster. So all he has to do is turn around, talk to the warning forecaster. Hey, we got golf ball size hail in Bennett. And, and we'll get that report real time as it happens. So we thank you guys for all the work that you do out in the field. And we hope we have a strong relationship with you all in the future. Another way we can get ground truth is from CoCoRaHS. And if you're not familiar with CoCoRaHS, it stands for the Community Collaborative Rain, Hail, and Snow Network. And it started after the Fort Collins flood back in the late 90s. Started a very small project, just covered like Fort Collins. And now it's huge locations. And we work very closely with the group. And so we're getting all those rainfall, hail reports from CoCoRaHS into our local National Weather Service office. If you're not want to be involved, hey, you get these nice, cool 4-inch diameter rain gauges, and you report your weather pretty much every morning at 7 a.m. And it's a great program. You can compare precipitation amounts. Here's a map of Weld County, a little bit of Larimer, and all those individual numbers are all the individual stations showing their rainfall from the last 24 hours. So great program if you're interested to get involved with them. All right, and so once you're making your report, we give you guys a couple of options. And probably the best option is through our dedicated severe weather line at 1-800-287-2498. If you're local Denver, you can just use our 303-494-2884 line. The second option, you can actually send a report through the web. And don't worry about writing all these down. Once I get your emails, I'll have these handouts available with the phone numbers, website addresses, all the things you might need. Once you click that second link there, you'll get to a series of links. You can submit, report. You can send us information through Facebook and Twitter. Good things for that would be like, if maybe you've taken some video of a storm, hail, flooding, whatever, and you can send us that, and that helps to complete our storm history. And then, of course, we are monitoring the social media. Sometimes on a busy evening, that's almost a one-person job where there's just tons of reports coming through Twitter and Facebook, and it's great. We can never have enough information. Again, reporting procedures. The big thing is, and it all boils down to the safety part of it, maintaining your situational awareness. What are the storms capable of producing in that given environment or on that given day? So is it a tornado day? Is it a hail day? Is it a flooding day? Or maybe it's all of the above. The next bullet is, when in doubt, give a shout. So we've had spotters in the past where they have not called us because they just, they really weren't sure what they're looking at. Am I really looking at a tornado, or is that just some dust swirling around? We can help you make that call. So you could call us, tell us what you're seeing, and then we can look at our radar and kind of back that up and maybe put those pieces of the puzzle together and kind of make a general consensus what's going on. So even if you're not sure, give us a call. Don't be afraid to do that. Where are you? Location. Location is important. Even if you're not at your home location, you're out in the field, we'll use, you can use your lat long, mile markers if you're on the highway, cross streets, any of that stuff will work for us. So reporting location, giving your spotter number, and detailed report. Things to report, and this is just a smaller list. When you guys get the guidelines, they'll be much more complete, a little bit more detail, but these are some of the biggies. Hail, anything half-inch diameter or greater, wind gusts above 50 miles per hour, tornadoes, funnel wall clouds, heavy rain, flooding. And if you say you're in Denver metro, you're getting an inch of rain in an hour or less, and that usually, as a rule of thumb, can create some flooding. Or if you're out in the rural areas, maybe you're out in Bennett, so it's 1.5 to 2 inches of rain for a rural area. That's kind of just general rules of thumb that we use. Of course, any kind of storm damage. And to also note, hey, we're not just summer severe weather. This is a full year program, and so wintertime, if you've got heavy snow, wind, fog, freezing, drizzle, all those reports are very beneficial to us. All right, and finally on reporting, again, in priority, this is the best way, obviously, through our 800 number. You want to send a report on the web, this is your second best way, and this is kind of more after the fact, more of a historical kind of view. You got to your house an hour later, it's, oh, wow, I've got all this hail on the ground. So you can then report that. Sending pictures and videos is good also for our storm history. And then, of course, through CocoRaws, we look at those numbers quite a bit as well. I'm not going to go into a lot of details on how you do all the sending reports on the web, but there is already a YouTube video online. I'll have this linked on our website as well. So you just click on that. It's about 20 minutes long. Just kind of navigates you through sending that report, also through just some of the basic things on our website, and also gives you some information on the Storm Predictions website, because we will talk about a few products that we have you look at from their end as well. All right, so that's it on the reporting side. Moving to a little bit of safety items. And this is a chart showing nationally weather fatalities, and we're going to focus on the thunderstorm related ones. That would be including the flood, the lightning, tornadoes. And if you look at the yellow bars, these are the 30-year averages. More people die from flooding across the country than any other weather phenomenon. followed by tornado and lightning. Well, that's nationally, but Colorado kind of fits into a different structure. And unlike flooding, which is the big one for nationally, for Colorado, it all comes down to the lightning. And more people die from lightning in Colorado from thunderstorm related than any other weather phenomenon. And historically, this map shows from Vaisala that Colorado is tied fourth for the most fatalities across the country. This is from data all the way back from 1959. And so we do worry about the lightning a lot. We usually average 2 to 3 fatalities every year. Last year in 2019, we only had one fatality. That's still one too many. We did have some injuries, and of course, we deal with lots of cloud to ground lightning. So if you want to try and avoid becoming one of those statistics, it might be happen to look at this lightning casualties time of day chart. It was compiled by our office down in Pueblo. And as you can see along the bottom line here is the time of day. And boy, you send your eyeballs over to about 2 p.m. and that's where it peaks across Colorado. So more people die at 2 p.m. in the afternoon from lightning than any other time of day. So what can you do about that? Well, if you're going up hiking the mountains, it's always good to get that really early start, sometimes, way before daybreak, because if you're climbing that 14er, you want to certainly be down off that mountain before 10 o'clock, because look at here, you start getting these fatalities after 10, 11 o'clock in the morning. And I guarantee some of those early fatalities are from mountain climbers. The things you could do, plan ahead, monitor the skies. Hey, if you're starting to see those cloud buildups and you're only halfway up the mountain, yeah, maybe it's time to think about making a return trip and making another turn at the top on another time. Just adjust your activities. We did have one lightning fatality. This was last summer, Bear Creek Ridge Trail southwest of Boulder, about 1 in the afternoon. It was a direct strike. And we kind of consider this a high-risk event because a couple of reasons. It was approaching the peak time and month of the fatality. It was along a ridge line. It was an exposed area. And yes, the fatality was male. Men, we take a bad rap, and maybe for good reason. There's like a 4-to-1 ratio of male versus female on the fatalities. Maybe it's that kind of that macho image that we've got. That, hey, you know what, we're not going to let a lightning scare us off from the golf course or the mountain range or the lake, what have you. All right, we did have a few other injuries. One was up at Rocky Mountain Park and another down at Devil's Head, where we had 8 injuries, 1 critical. For those that have ever done any hiking down in there, fairly steep little rock face there and a little lookout tower. From what I understand, this was at 3 o'clock. So again, mid-afternoon, prime time for lightning, June 30th. Climbers did attempt to take shelter, but it was really unclear where. And so we're not going to do a formal poll, but maybe you guys can think about where you would think you would be safest from this storm that was rapidly approaching from the west. Would you like to remain A, on the ridge line, B, move under this kind of little cave area or a cliff face, C, go up to this vantage point and this lookout tower to see exactly where that storm's coming so you can get a better vantage view, or D, descend down to the lower portions in these clumps of trees? All right, if you picked D, you are correct. That would be your safest bet. If you could get down to those clumps of trees, that's where you're going to be safe. A lot of, when we've done this webinar earlier, we have a lot of people that pick B, and it seems like B might be good, but if you're under this cliff face, it's not really going to protect you from that lightning, because lightning can jump from rock to rock face, and you would be just as accessible to that lightning as if you were probably even on the ridge. So D would be your best choice here. And then we got this picture. This is from Coors Field. Unfortunately, we can't be at Coors Field yet. Hopefully, we'll get some baseball going this summer. Maybe, I don't know. If you were there this particular day, 3 hour delay. And it's interesting. They had folks get under the shelters, but there's still a scattering of people, even though there's lightning bolts traversing the sky really close. And what we teach from the Weather Service, very simple: when thunder roars, go indoors, stop all activities. What I kind of liked here is on the jumbo screen, if you notice, I have a picture of the local radar. So good job, Rockies, for maintaining situational awareness for your fans. All right, and sometimes we call these bolts from the blue, because sometimes we generally ask folks to wait at least 30 minutes after the last audible sound of thunder before resuming activities. Because you might think, oh, the sun came out, the rain stopped, oh, it's good to go out and play. But then because of these guys, you see these bolts that can come out at the top of the storm, they could travel as many as 10, 15 miles away from the main parent storm. And even though the sun is shining, you may still get struck. So be aware of that. All right. Now we're going to try and do something fancy. I found this video, and if you're not familiar with Charlie Barron's, he's got some really cool stuff. And he did a little segment called What Not to Do, Dads During Tornadoes. And so I'm going to skip out of this presentation for a moment so I can pull up the YouTube, and we'll see if we can get this to work. So stand by. Charlie there got hit by the big old hailstone. We do have some hail hazards. Luckily, most people don't get killed by hail. But as you can see, this guy took quite a wallop on the head because, sometimes these bigger hailstones can go up over 100 miles per hour. All right, tornado safety. We saw what, Charlie's out there looking outside, looking for the tornado. That's kind of our human instinct. We want to go out and see instead of going to the basement like is our prime way of staying safe. Hey, we want to go out, take the pictures, get the videos, and sometimes we're putting ourselves in harm's way. So just a few things on that tornado indoor safety. Again, we want to be on that lowest side of the building, of your house, basement if you've got it. If you don't have a basement, some sort of interior room away from windows. The big thing is to protect yourself from flying debris. And then, of course, for those that have seen the presentation before, you recognize this house from Windsor that was partially destroyed from a tornado that went through Windsor. And if I had picked to take refuge around that garage, structurally, it's not as sound. And so I got a little bit hurt. And of course, by the windows, notice they're all smashed out. But if I had picked some sort of interior room away from the windows, I probably would have been all right. Because notice, the house is pretty much standing. It's good to go. So just a few things on that. Outdoor tornado safety. There's really no outdoor place safe from a tornado, especially parts that are bad. Bridges, overpasses, underpasses where winds can accelerate. These are definitely not good options. Sometimes we have things that happen like this, where there's all these big traffic jams under the underpasses because folks are trying to take refuge either from the heavy rain or the hail. But the problem is now you can't get safety vehicles through there, and you've created a problem. All right, one more slide on outdoor tornado safety. This is kind of a last resort, and if you noticed, I put in bold. Essentially, at this point, you're out of safe options. So you're at the point you're getting face to face with that tornado. What are you gonna do? You've got a couple of not as safe options. One, you could stay in your vehicle, keep your head below the window level, keep your seatbelt on. Or you can abandon your vehicle and get into a ditch or culvert. Again, the biggest thing, covering your head and your body from that flying debris. Now, obviously, these last two options, not necessarily either one of them is safe. Each one is kind of dependent on your specific situation, and it's kind of your own responsibility how you want to handle it. From this picture, either options probably did not work out. One, this vehicle got tossed around by this tornado pretty bad, and they're in this low-lying gully. Of course, it's full of water, so you're either going to get killed by the car from the tornado or you've drowned. So good luck there. Lots of praying would be needed. Well, if you're in your car, and usually not a lot of good things happen. I don't know. Personally, maybe I would take the ditch option. I can hold my breath and I can sometimes swim. But if you're in your vehicle, notice as this vehicle got thrown multiple times from an EF2 tornado. You can see the skid marks as from the tires as the winds rolled this vehicle over multiple times. And here's a UPS vehicle that did not fare very well either. Just a few things on flash flood safety. Water is a very powerful medium when it's moving. So it only takes about 18 inches of water can float some vehicles. 2 feet of water will float all of them. And if you're just out standing around in it, it's only about 6 inches of swiftly moving water. That's about ankle deep that can knock you over. And remember, nationally, flash floods is the #1 killer from thunderstorms. So our big slogans: turn around, don't drown. And of course, if you're in the mountains, climbing to safety is your best bet. There's a lot of uncertainty with water. Even if you're in the daytime, you're passing some county roads. And even from this picture on the left, it's maybe not completely clear how deep that might be. You might try and risk it, but do you really want to take that chance? And then, of course, on the right, nighttime flooding, it's really hard to see where the water is, where the roads are, where there might be water already over the road. Okay, that pretty much concludes the safety portion of the program. So let's get right into the meat of it and talk thunderstorms. So when we're cooking up a thunderstorm, couple of things. We usually need about 3 ingredients. So just like if you're in your kitchen making a cake, we can make our own thunderstorm with just 3 basic ingredients. First is moisture, especially close to the ground. We're looking at humidity, dew points, and that acts as a fuel for the storm. Just like your car or truck needs gasoline, fuel to run, thunderstorms need fuel, and that's the moisture. Instability. This is the tendency for air to rise on its own. We'll talk more about this here in a minute. And lift. We need a mechanism to make that air to start to rise. So for the moisture, there's several moisture sources that we can get moisture into Colorado. One is low-level moisture, even all the way from the Gulf of Mexico. So if the low-level flow is, say, from the southeast and east, and then some of that moisture will eventually advect back into Colorado. And so that'll help fuel the storms. And then we can also, of course, get moisture off the Pacific Ocean from storms coming from the west and southwest. Instability. And so if we look at instability, take this hot air balloon and pretend that's a parcel of air in your thunderstorm. And if that parcel is warmer than the environment around it, it's going to be able to rise, just like a hot air balloon does. And essentially, this is the kind of situation we need for thunderstorms to grow in. If we look at stability, it's good. This is kind of an easy way to picture it with these 2 pictures that I'm showing you now. On the left side is what we call an unstable environment. And you can see the smoke plume, probably some big fire, and notice that plume is going up, 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 and there's really nothing to stop it. It just keeps rising. So this is an unstable environment. This is the kind of environment we like for thunderstorms. Unlike this picture over here you see on the right, notice this little steam plume here. It rises up a little bit, and then notice how it really shallows out. And so what's going on in the atmosphere there? Well, if you think of stability as maybe a pot of boiling water on the stove, and you've got a heat source like the sun, or in this case, the stove, it heats that water in your pot, and notice the steam beginning to rise. There's nothing really trapping that steam from going up. And that would be an environment unstable for thunderstorms. But what happens if I put a lid on that pot, is that steam going to continue to rise? No, and you can see how it's being trapped from going up any higher, just like if I put that lid on that pot. And that's a stable environment. And a lot of times, most of the winter and in the early morning hours, we are usually under a stable air mass. And until the sun begins to heat it and it dissolves these low level stability issues, or what we call inversions. Inversions are when temperatures increases with height. We don't want those for thunderstorms. But a lot of times in the mornings, we have these inversions. And until the inversion dissolves, will we be able to get thunderstorms? And so that's why it usually takes till early mid-afternoon to dissolve those low-level inversions until we get enough heating to begin to pop those thunderstorms. Okay, let's talk a little bit about lift. We need to be able to get that parcel lifting off the ground. We can do it by a variety of mechanisms to lift that air. One is by a good old cold front. And in this animation, you can see this wedge of colder air. And as it meets the warmer, moister air on the other side, you get this convergence of air masses. And you begin to see these clouds begin to build up. So that's a cold front. We can do it by warm fronts, but warm fronts really aren't that common across Colorado. If you live back east, you have quite a bit of warm front lifting mechanisms going on. Low pressure area, if you guys remember our bomb cyclone back in March of, what was it, 2019, that provided a ton of lift for those big heavy snow and blizzard conditions. Dry line is another big one for the summertime. So in this example, see all these white clouds, and this is a lot of warm, moist air that's advecting from the Gulf of Mexico and into portions of Texas and Oklahoma and Kansas. But notice how dry the area is on the west side. So you have this dry air intrusion, and so you're having a clash of air masses between very dry air on one side and very moist air on the other side. We call this a dry line. And a lot of times this is a focus for dry line thunderstorms across eastern Colorado. A lot of times noted by this green dash line, a lot of times we see this is like a focus area for thunderstorms along our Colorado-Kansas border areas with some sort of upper level disturbance off to our west. We can get lift from upper troughs and disturbances. Jet streams will do it, and thunderstorm outflow. So you can see in this thunderstorm complex, as it builds, notice it's sending out this circular outflow. And we'll see it one more time. And then as its outflow develops, you can see it hits other storms and develops additional thunderstorms. And that creates additional sources of lift. All right. Another one you can see is with upslope. And you've probably heard the term upslope maybe mentioned on the local TV news. But upslope, all it is if I've got a wind direction, and say we're here down here in Denver from this picture, and if the winds are some sort of a easterly, northeasterly component, and those winds coming from the east, as they hit the mountains, the terrain it's forcing that air to rise because it has nowhere else to go. So as that air rises, it cools and condenses and then produces clouds and precipitation. So upslope is a fairly common thing that we see here with our terrain differences across Colorado. And especially say you live in Denver during, say, it's snowing out in the wintertime in January, and then you're, say, traveling to Boulder, and you maybe have 2 inches of snow in Denver, but by the time you get to Boulder, it's like a foot of snow. And that's just that enhanced upslope component that we see from these strong easterly winds. Well, this map shows where it's always upslope somewhere, and it's always terrain dependent on wherever you are. So like when we talked about Denver, notice the yellow arrows anywhere from the east, northeast is upslope. But say you lived in Fort Collins and your upslope prime wind is from the southeast. And that's because you have higher terrain up here to the north up the Cheyenne Ridge, which is over 6,000 feet. On the other spectrum, say you live down in Monument or Parker, and notice the prime upslope wind there is actually from the north or even northwest. Because now you've got higher terrain south of Denver, and you've got like a 2,000-foot climb from Denver to the top of, say, the Palmer Divide, where you have elevations above 7,000 feet. So you can really see how the terrain that we have here in Colorado really plays a big impact on what kind of weather is happening. And then, of course, every afternoon on a June, July day, you can look out west to the mountains, and like clockwork, you can begin to see the clouds building up from these developing thunderstorms because of the mountains and the lift that it's producing from upslope flow. Okay, so we've talked about our three ingredients, our moisture, lift, and stability. Now let's get into different thunderstorm types. We can have we call single cell or pulse storms. We can have multi-cells in lines, and then of course our big boy supercells. So we'll talk about each of these. We'll take them one at a time. Now first with our single cell storm, we're going to start over here in the far left. And we call this the towering cumulus stage. And you notice here the red arrows, this is an indication of the updraft. So the air is going up into these developing clouds and these towering cumulus. But at this point, there is no precipitation falling. So there's no rain, there's no hail. It's just kind of building from the cloud base level and going up a little bit. And you can notice these cylinders below. This updraft cylinder is noticed by the red cylinder. Now, visually, if you're out in the field spotting storms, that towering cumulus stage might look something like this. And so you can have this nice, we call this rain-free base, so there's no precipitation falling underneath it. It's all updraft, and all these clouds are building and building in this, what we call the towering cumulus stage. Well, now as we turn our attention to the center slide, notice now we call it the mature stage of your thunderstorm, because now I not only have this updraft with the red arrows and this nice building cumulonimbus thunderstorm, but now all those droplets in ice or whatever's in that storm is getting too heavy for that updraft to support it, and then begins to fall back to earth as we call the downdraft, and notice by these blue arrows here. And so then the downdraft, it'll be all your rain, your hail, your wind, anything that was in the cloud has fallen back down, because in nature what comes up must eventually come down. And visually it might look something like this. And so maybe your updraft is on the right hand side where my cursor is, and notice all the white fuzziness, and that is your downdraft, where there could be a nice little hail shaft in through there. And that's your mature stage, where you have now your red cylinders, your updraft, your blues, your downdraft, but the things are almost on top of each other. Because now as we get to the dissipating stage, notice now that yours essentially is downdraft dominated, and your clouds are not as well defined. They're more kind of, I would say, wispy looking, and you're just left with a kind of a wimpy looking storm. Visually, maybe it looks something like this. And so again, that wispiness, you notice your cloud edges are more smooth, they're not as defined as, like, say, we saw in the mature stage, like through here. And then, but you still have a downdraft, so it's raining or hailing and through here, but that's pretty much about it. It's downdraft dominated, noted by the big blue cylinder, not much left of your updraft. So that's kind of your three-stage thunderstorm cycle that each one is going to go through during its lifetime. Here's a picture that we had sent from one of our spotters, and I like to look at this as kind of maybe the kind of the transitioning stage between the towering cumulus and the mature stage, because, boy, you've got a nice rain-free base updraft, well, nice defined cloud edges, and then a developing downdraft where right about where my dash line is, that's kind of probably the edge of that downdraft. It's probably going to start raining there here probably in the next 5 or 10 minutes or so. But a good example of that transition stage between towering cumulus and mature. All right, so with our single cell storms, just a few bullets to characterize these guys. Typically, they have weak winds aloft. And so meaning these towers are going to go straight up and down. So a good example of this single cell would be this storm tower over here that you see on the right part of your screen. Where notice the storm tower is straight up and down, and I'll put a little dash line to indicate that. Typically, these are going to occur just during your peak afternoon heating. You're going to get an intense updraft, well-defined cloud edges. Think of your favorite vegetable, or for me, not so favorite, like cauliflower or broccoli. Not really a fan of either one, unless it's got cheese on it or something. And then you're going to have a collapsing downdraft, but it's going to be quick. It's going to be short duration, 5-10 minutes. Because, what do they say in Colorado? Wait 5 minutes, the weather will change. And this is your definition of your single cell pulse storm. With multi-cells, they're the most common type, and they're made up of a series of up and down drafts. And you can see this by these up by blue arrows, the up drafts, and then down, and another tower going up, and another down, and another up. And there could be a whole series or clusters of these guys making up this multi-cell thunderstorm. Now, each individual cell may only last that 20 to 30 minutes, but your entire life cycle might last several hours. And I'm going to skip to this slide. This is a radar presentation of a linear multi-cell, like a squall line, where these lines of storms can be hundreds of miles long. The main threat with these is typically your straight line winds, generally up to about 30 miles per hour. And sometimes we can get what we call these bow echoes. And this is where a portion of that line of the storms begins to bow out. And you can see I dashed this kind of bowing out where you can see from this line where it's accelerating ahead of the main line of storms. And this is where you're going to see your strongest winds up to 100 miles per hour. And to kind of, over the last 10 days, we've seen several, with severe weather so far this summer, it seems like we've had more wind than hail or tornadoes. And we had an event June 6th and June 9th where we saw a lot of these linear features that did create, we had in Washington County a lot of damage over in Akron, where we had a wind sensor that was clocked in over 103 miles an hour. So definitely these linear storms can cause quite a bit of damage. All right, let's talk a little supercell. And now with a supercell thunderstorm, we're dealing with not just any updraft, but now we're seeing that updraft beginning to rotate. You have rotating updrafts. This also will help transport your precipitation away from the main updraft, and this was going to allow your storms to survive over longer periods of time. These supercells are the ones who are going to see your largest hail, your longest track tornadoes. All right, so with supercells, let's talk a little bit more in depth. And just like with regular routine garden variety thunderstorms, are 3 ingredients of moisture, lift, and instability. We're going to add a 4th one, and it all revolves around the wind. And specifically what we call shear or wind shear. Typically with supercells, we'll talk about 2 types of wind shear. One is speed shear, and that is showing the winds increasing with height or increasing as you go up in altitude. We can also see directional wind shear, where the winds are changing direction as we also go up in altitude. Now, how is this going to affect supercells? Well, remember our up and down draft cylinders in a single cell or weakly sheared environment. So say this example here on the left, it's got weak winds aloft, maybe it's only 10 miles an hour, and your up and down draft cylinder almost on top of each other. So it's like when we talked about our single cell pulse storms, It goes up, it goes down, and then it dies. But what happens if we increase the wind from left to right? So we have stronger, so instead of maybe 10 miles an hour, we now have 40 miles an hour of winds coming left to right. Notice what happens to our up and downdraft cylinders. They're now, our downdraft cylinder is displaced downwind. And so now our up and downdraft can maintain coexistence, maintain in harmony, and then that's going to allow for your longer duration storm. We can further exemplify this by our favorite backyard water toy. And I'm sure with these hot days here, we've had that good fun times to get out the water toys and play and get wet. So in this example, say it's the middle of the morning, it's a calm, it's sun's heating up already, and I got my water hose out, and that water hose is going straight up. And let's pretend that water coming out is our updraft. Now, if I'm standing right under there, I'm probably going to get wet because that water is going to come right back down at me through gravity, right? But what happens if I increase the winds, say from left to right across my screen? What do you think is going to happen to that water? And voila, now, say I'm underneath that water hose, I might even stay a little dry because now here's your updraft. That wind has displaced your downdraft further downwind. And so now you can have both going on at the same time. Well, let's look at a real storm and show you how this all gets put together. So here is our nice thunderstorm, and this is a time lapse from Michael Blinsky from Vorticity 2, he named it. And you're going to see a lot of examples from him. And he's got a lot of great stuff. You can probably Google him on YouTube and find all his really cool thunderstorm videos. But in this example, we have a thunderstorm. And say our winds here at the cloud base are maybe 20 knots, or about 25 miles an hour. But in your mid-level part of your storm, they're much stronger. They'll say 50 knots or maybe 60 miles an hour. And so because the winds are much stronger aloft, notice now the tilt of this storm tower. It's not straight up and down. Remember when we were looking at that single cell storm, but now it's tilted. And that's all because of the speed shear. And notice now your downdraft, notice by the blue arrow, is well displaced away from your updraft. So this storm's probably going to maintain itself for a little while. Okay, here's an animation showing directional wind shear. So in this example, notice these clouds closer to you, kind of going left to right across your screen. Those are lower levels. And then notice the clouds above that level actually moving in a different direction or coming right towards you. So you can actually see directional wind shear going on in the atmosphere. We can further exemplify the role of shear with supercells by looking at this three-section schematic. And if we start over here in the far left, notice this kind of red tube thing. And you can kind of play along at home. So if you've got a pen or pencil handy, put it in your left hand, and it's just kind of sitting there, right? But say the right hand is your wind, and the wind, say you bring your right hand and it comes just above and it touches your pencil. What is your pencil or pen going to do? It's going to begin to roll. And so that's what we got going on in the atmosphere. We got these what we call horizontal rolls. Now, if one of these horizontal rolls starts to get under an updraft, notice by these green arrows, your horizontal roll is now getting tilted into the vertical. And now I've developed this rotating updraft. And this is going to lead to our supercell rotation. So visually, let's show you some clouds, so how you can put this all together. Now with our supercells, the first feature you're going to be able to look at is what we call the mesocyclone. And the mesocyclone is kind of your mid-level part of your supercell, and it's just rotating like crazy. And so cloud feature is what you want to look for. And so this example over here on the right, this is from 3 distinct supercells that were chugging along Weld County in 2017. And at least from this supercell in the foreground here, notice the cloud striations, kind of this corkscrew appearance. And that's telling you as spotters, this visual cloud indication is, hey, there's a lot of rotation going on in this storm. And here's some more examples. So again, you can see the striations, the corkscrew appearance from this supercell mesocyclone on the left. And then also from a different storm, again, you can see them right in here, these striations, these layered effects of clouds, and this is all rotating. And here's again time lapse from Michael Blinsky showing us a rotating supercell. And you notice this whole baby is rotating, and most of the time, because we are in the northern hemisphere, that you're going to see these most of the time a counterclockwise rotation through these storms. The second feature we're going to look at with supercells is the wall cloud. And the wall cloud you're going to see usually under the rain-free base, under the updraft. So our updraft is here. Our wall cloud is kind of outlined, and it's kind of this blocky, low-level appearance behind or below your main rain-free base. And this is where the air is up, the updraft is coming in really strong. This is where you're getting the abrupt lowering of these clouds. And these are important because sometimes it can be the precursor of a developing tornadic storm. So as spotters, you want to watch for these wall clouds, watch for these beginning to rotate and become persistently rotating on the order of minutes and not just seconds. Here's another picture of a wall cloud. Notice again the kind of the lowering blocky appearance. And a lot of times you'll see a slope downward towards the precipitation area where I'm circling with my cursor. So wall clouds will slope towards the precipitation. Again, you want to look for rotation with these guys and report these to our office. Now here is an example of a wall cloud right in here. Notice the lowering cloud. This is courtesy over from our Viero Cam network through Viero Cams and Mike Nelson over at Channel 7. And so you can see here again. Now, you start to lose it. You lose sight of it in through here because what's happened here, your outflow, your downdraft has essentially probably obscured your wall cloud because the wall cloud may actually still be there. So always be kind of on the lookout. Be careful for that. Because also there could also be a tornado. So if you decide to drive right through there to see, oh, I get a closer look at that wall cloud, well, maybe by the time you get there, already a tornado is developed, and then you'll be in Dutch. All right, let's put the whole thing together. So here's our big old supercell, the red arrow indicating our rotating updraft. Wall cloud under that rain-free base, under the rotating updraft. And again, this is where you would likely see the position of your lowering wall cloud and or tornado under that updraft. Your downdraft is down here off to the right. A couple other features we'll talk about later in the program is this flatter looking anvil cloud and then your overshooting top up here. Sometimes we get these flanking lines. You can get developing multicells all up along this line. Here's just another example of another thunderstorm showing the rotating updraft, rain-free base down here, and your downdraft off to the right. Here's some more supercells, again, visually showing you these striations. So certainly if you see one of these guys, you say, dude, I'm looking at a supercell because I can see mesocyclone, I can see the striations. Michael Charnick, who took the picture, works at our Grand Junction office, and he's quoting this with beef for the side of pancakes. So you can always think of supercells and mesocyclones as pancakes. Oh, I got a big stack of pancakes. All I need is a little maple syrup, and I'm good to go. Sometimes with these supercells, you'll see this inflow band that you can see off here to the right. So otherwise known as a beaver's tail. And this next picture will show that a little bit better. So you can see the beaver's tail, and through here is like the inflow band that's getting sucked in with this really strong updraft into this supercell. And from a mic, here is our rotating supercell, striations, the rotation, rain-free base, your downdraft off to the right, all of it in play here. All right, the third feature you're going to be able to visually see as spotters is what we call the rear flanking downdraft, or RFD. And your visual key here, and notice by these blue arrows, notice how the clouds all through here are becoming brighter and whiter. Well, this is an indication that that rear flanking downdraft is rotating through the mesocyclone and probably is rotating through the front part of this storm. So your visual clue again is this brightening of the clouds. And again, some of the research in the past has shown that this is one of the key features that may be developing before a tornado begins to develop. So kind of watch out for those. Here's a 4-panel example of this RFD development. You're in your upper right. Notice the clouds right up in here are becoming a little brighter. Even brighter still in this upper right-hand shot. And this eventually develops a full-fledged tornado on the ground before eventually it begins to what we call the roping out, or the weakening, becoming a funnel again. And typically with these RFDs, as they rotate across the storms, they will cut off that inflow and eventually cut off that fuel that's been driving this tornadic storm. And here's some more speedy pictures showing a tornado in action, but you can see the end part where it kind of weakens. I'll play that again. And notice how it weakens, and we call it, there's into that roping out stage we talked about. All right, let's take a look at the storm structure from the top view. And with that, we're also going to have a little help from, notice my favorite little stick guy, Spotter Dude, down here, and he's going to help us. He's going to be down here on the southern quadrant. He's kind of in the inflow side of the storm. And we'll kind of go through the schematic. We'll start here where the T is. T stands for tornado. And again, it would be under the rotating updraft. Notice your rear flanking downdraft would be rotating around to the back side of your tornado. And up to the north and northeast quadrant of the storm, that is where your heaviest precipitation is falling in what we call the forward flanking downdraft. Now, say, and this would kind of correspond to our corresponding radar. So the T tornado here would kind of correspond right about in here, where there's actually what we call a hook echo. And in the old days of weather radar, the hook echo was our main way of figuring out, hey, this is a tornadic storm. Well, now with Doppler radar, we can do a little bit better than just finding the hook, but this makes a nice example. And with radar, noticing the bright reds, this is where your heaviest precipitation is. It's probably where your big hail is, just off to the north and northeast quadrant of where that tornado would be. All right, so now let's take Spotter Guy and let's have him vision looking to the northwest. So ideally, if we were following our conceptual model of supercells, I would suspect we should be able to see the tornado and maybe even a rear flanking downdraft if there was one. And so with this example, yes, we do. So we're looking up, and yes, we can see the wall cloud lowering. Notice the little appendage, the funnel, probably a tornado in through here. And then notice the brightening clouds here. So you have your rear flanking downdraft. So that works out just about right. But what happens if we go way over here to the right, and now Spotter Dude, he's looking off back to the west to our front edge of our forward flanking downdraft, where the leading edge is. what kind of clouds and things should he be looking at? And typically it might look something like this. And the cloud feature we're looking at is what we call a shelf cloud. And you can see the shelf cloud is a linear feature, and it's kind of outlined here. Notice the kind of the real grayish, that's all your precipitation that's falling just behind that leading edge of the shelf cloud. Here's another picture of our shelf cloud from one of our spotters, right in through here. You have that cool outflow air ushering in right behind it. So if this storm is coming right at you, you'll eventually get hit by that wind and rain pretty darn quick. With your shelf clouds, a lot of times your clouds will slope away from the rainfall area. And normally they'll be associated with straight line, strong damaging winds, not necessarily tornadoes most of the time. Here's a few more pictures of shelf clouds. So right in through here, right in through here, a nice one. And then from Vorticity 2, you're going to see a few shelf clouds. We're kind of underneath here, but right in through here as it comes towards you. And also right here, this is a cool one. There's your going from left to right, shelf cloud back and through here. And notice it gets really fuzzy. Here's your rain, wind, and hail ushering in right behind it. Well, we can do a kind of a side-by-side look between, just so we make sure we get the picture between your wall and your shelf clouds. Again, your wall cloud is much blockier in appearance, unlike your shelf cloud, which is much more linear, as we can see here. And also is associated with your storm outflow, unlike the wall cloud, which is more on your inflow side and under that rain-free base. Again, the slopes are different. With wall cloud, it'll slope towards the rainfall area, and with your shelf cloud, it slopes away from the rainfall area. So hopefully that makes sense. Another cloud feature you'll see with the downdraft and outflow is your roll cloud. These are you're probably not going to see as often, certainly not as much as your shelf cloud. And the main difference here between your roll and your shelf cloud is that the roll cloud is not attached. There's a detachment from the main parent cloud above. Where your shelf clouds are attached, the rolls are not. And here's an example of a roll cloud. And you can see it's kind of rolling, kind of doing its own thing. Most of the time not attached to the cloud base above. All right, still talking outflow and downdraft. Another big one that we could see here across Colorado is microburst, straight line winds, where you can see winds certainly in excess of 60 miles per hour. So this schematic, as that wind impacts the ground, notice it kind of curls above, it impacts and then curls around. And this is noticed by this spotter picture here. Here's your downdraft, and notice impact, and notice how it curls around here. So visually, that's going to tell you, oh, I got some pretty strong winds there. And for example, these microbursts, here's a good one. This was taken down in the Tucson area. Notice nice thunderstorm here. You're getting some rain shaft. Watch closely. It zooms in the middle part of your picture. And you see that big ball, boom, and impacts. That is your microburst. That it's probably creating at least 60 miles an hour. Here's a kind of a slow motion. That'd be pretty incredible. We do tend to get a lot of microbursts. They're very small in coverage, usually less than 2.5 miles. They're kind of hard to see on radar, so we do need help from spotters on seeing microbursts, but they do create some impact. And then going along with this same theme, first let's look at this picture on the right that I took from my neighborhood not too long ago. But notice all these kind of streaks, and if you're not careful, you might think, oh, there's a bunch of funnel clouds there. And yes, in the past, we've had spotters that will call these in as funnel clouds. But what this really is virga, or it's rain that's evaporating before it hits the ground. And this is a feature we see is pretty common here along the Front Range because our atmosphere is can get pretty dry here in the low levels, especially what we've seen lately. There was another virga shot up here. This was up in the mountains up in Summit County. Okay, well, when we're out spotting storms, a lot of what you will see is going to be dependent on a number of factors. And one is what side of the storm you're on, how far you are away from the storm, visibility issues, not usually much of a problem here in Colorado. Maybe we got to deal with, yeah, we have had some haze and smoke here across the area from forest fires the last few days. Maybe we got some blowing dust. Yes, we've had our share of wind. Trees, things, buildings, other storms can also maybe impede what you're seeing. But our primary goal going forward is safely determining that strength and rotation of that updraft. So back to our familiar top section of our supercell. And as we remember, we're going to start our spotter dude down here in that inflow sector of the storm. And as we noted before, if we're looking northwest, and if it follows our conceptual model, we should be able to see a tornado. And yes, we do. But what happens if he's way up there on the northern part of the storm and he's looking back to the south? Will he be able to, you think, see that tornado? Well, the answer is probably no. And the reason for that is now he's looking through essentially the biggest portion of the downdraft where there's the biggest hail, the wind, and all that crap. So if he's looking south, he's just probably seeing it's dark. It looks kind of ominous. I don't want any part of it. However, there are chasers out there who will do whatever they can to get face to face to that tornado. I would highly advise not doing that because on a couple of reasons. And what they do, they call this core punching, where you drive your vehicle right through the biggest hail and rain and wind and to get to that tornado. Not good thing to do that. You're going to get your vehicle pounced upon and you may get face to face with that tornado and something you may not want to do and may later regret. All right. So now let's take a look at some farther away distances, what we're going to see from our upper level, mid-level, and upper level parts of our storm. And so maybe now you're up to 50 miles away. And in this example, we're looking towards Last Chance in Washington County. And we're looking at we can still see the storm tower, but we're going to focus on these upper levels, that cirrus anvil and the overshooting top. Well, that anvil is kind of this flattish looking pancake cloud. And what's going on here with the atmosphere is that updraft is going up and up and up. As it gets high enough, it's coming against some resistance, some higher level stability that's kind of putting the brakes on the updraft. It's slowing things down. It's getting a little sluggish, and it kind of flattens. It makes this kind of cirrus anvil. But if your updraft is strong enough, it's able to punch through that higher level stability, and now you get these overshooting tops. And so as spotters, if you see that, that's going to tell you, hey, I've got a really strong updraft of this storm. Now, this example from Viero, in this time lapse, we can see this anvil noted by here. And if you look really close, there's some of these little bubbles. These are these overshooting tops. Again, indication of a very strong updraft. Now, the storm looked probably a little stronger right up front. Really nice defined cloud edges. It appears to me like it's been weakening over these last few seconds. But anyway, a really good example of your anvil and the bubbling tops above. Another cloud feature you'll see with the anvil on the underside of it is what we call mammatus clouds. This is associated with the anvil on the underside, and they develop from sinking air in the clouds and develop these little mammatus, these little pockets or pouches roundish clouds that you can see. They can be associated with severe weather, but not necessarily, and it certainly doesn't mean that you're going to see a tornado with it. All right, well, maybe we're a little bit closer to the storm. We're seeing now maybe this main storm tower. Yeah, you're 10 to 20 miles away. And again, you were looking at these well-defined cloud edges. Remember our broccoli and our cauliflower. And this is an indication of, again, a pretty strong updraft. Just like with your main storm tower here on the left, with this flanking line over the right, notice how your really small little towering cumulus, they begin to stair step and get bigger and bigger and bigger until they get swept into the main updraft. Again, indication of strong updraft. Some other accessory clouds you might see, especially with your downdraft and shelf clouds, is what we call these scud clouds. And scud clouds, they kind of dart in and out of existence. They don't hang around very long. They dissipate rapidly. Sometimes these can get misconstrued as maybe a funnel or developing tornado. But the main difference is these scuds are going to disappear pretty quick. Unlike if you were dealing with a sustained funnel or tornado, it's probably going to hang around a little bit longer than what we see with these scud clouds. And also, typically, we're going to see the scuds mainly on the leading edge of your downdraft, right behind your rain core that's sweeping in behind it. And remember, if we're dealing with tornadoes, or especially with supercells, it's going to be under that updraft portion of the storm. So if we're talking shelf cloud and you see this, think scud and not necessarily tornado. Speaking of tornado, let's talk a little tornado. And we'll get through a little bit of a ho-hum definition: rotating column of air in contact with cloud base down to the surface. I know I should sound more excited, but we'll get more excited. Anyway, but a lot of times you're not going to see that whole visible condensation funnel, but as in this third bullet here, a lot of times you'll see it with circulating debris or dust on the ground, like we see here where my cursor is at the bottom part, where the rotation is actually extended all the way down, and we can see it with this debris and dirt. Okay, so here's some more time lapse. And as spotters, if I ask you, you don't need to attend spotter training to know, dude, that's a tornado, that's a tornado, that's a tornado. These are easy. Unfortunately, a lot of the tornadoes that we deal with in Colorado don't always quite look like that, with the exception of a couple. And a lot of times as spotters, we're scratching our head trying to figure out, what am I looking at? And so this next portion of the slides are going to be dealing with what are we looking at. Well, first of all, did you guys know that we have our own tornado alley right here in Colorado? Typically, if I ask you where Tornado Alley is, you would say, well, Kansas, Oklahoma, Texas, but never really thought of Colorado. But if we look at our, well, there comes our Tornado Alley. And if we, I'm going to ask you a question, and you can, we won't do a formal question, but so which county in Colorado do you think has the most reported tornadoes since 1959? And I'll give you a few seconds to think about it. Here's our options. You could say Park, Well, Denver, Kate Carson. And I will tell you the answer is Weld County. So if you have any Weld County folks out there this evening, you are the winner, ding, 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 at 285 tornadoes since 1950. And guess what? That is more tornadoes in that county than any other county in the United States. So Weld County is the big winner. But notice there's some big numbers also as we go into Adams County or Elbert, Washington, Lincoln. And there are some factors that are going on why these numbers are higher. And I'll just kind of tease it for now, but there are some meteorological and reasonings why this is. Before we get to that, first we'll show you some different types and sizes of tornadoes that you may encounter, from the more common, probably rope or pencil tip tornado like you see over here, very skinny looking guy, to our cone or elephant trunk tornado, and then to our, oops, there we go, our wedge tornado. And this is a picture of a wedge tornado. This was the Windsor tornado, which was an example of a wedge one, where wedge meaning this is it's pretty wide at the bottom. So some of these diameters can be several diameters across with these wedge tornadoes. Sometimes they're harder to detect, meaning you might think it's just a big blob of rain coming at you until you start noticing, oh, the whole thing is rotating. Anyway, so the wedge tornado is typically a supercell variety, like we see here with wall cloud and all the works. But there's another cat, and it's called the non-supercell or land spout tornado. And it might look something like this, much different than the supercell, where this thing looks like it's coming out a bunch of just towering cumulus clouds. Remember, we talked about that first stage of thunderstorms, where the clouds are just developing. And these are where these land spouts can typically form in these early stages. So here's kind of a side-by-side comparison between supercell and non-supercell. And so far in the program tonight, we've been focusing most of our attention on the supercell, but we need to also pay attention on the other side, because this actually can be more common here along the Front Range. Because with the land spout, I'm not going to see this storm rotation and mesocyclone that we were talking about with supercells. They will typically follow or form early stage of development of a thunderstorm, unlike your supercells. If I'm watching the radar, I'm typically going to look for these guys on a boundary, or maybe it's an old front, that kind of thing. Unfortunately, they're harder to see, and I have usually much higher or lower warning verification, unlike the supercells, which they're pretty easy to see. The good news is, since even though we have a lot, the tendency is to be on the weaker side. And if we look at the enhanced Fujita scale, and this is the how the Weather Service measures tornadoes, and we all base this on damage. That's why we always do storm surveys afterwards to see what damage was, and then we can rate these based on damage to get that wind. And typically, with your land spout non-supercells, they're going to fall in that, usually in that EF0 or EF1 range, up to maybe 110 miles an hour. In comparison, the Windsor tornado was up to an EF3, and that had about damage up to about 163 miles per hour. And the good news is, at least in recorded history, Colorado, we have not seen any EF4 or EF5 tornado. Phew. All right, I added a couple bonus slides because this is fairly interesting, and actually, as meteorologists, we're learning some new stuff too. So I thought I'd share some of this on evolution of tornadoes. Historically, as meteorologists, and we pass this along to you folks, with supercells, it was always thought that tornadoes form from the top down. So, so far, we've talked about supercells and the mesocyclones. It develops a funnel, rear flank downdraft, and all of a sudden, boom, I've got a tornado on the ground. Now, on the other scale of things, when we talk non-supercells or land spouts, we always consider it a bottom-up approach, where the tornado develops from the ground surface and builds up to the cloud base. Well, there's a lot of new research coming out that's debunking this top-down tornado genesis information, and so a lot of it's been done by Dr. Jana Hauser, and she really looked at the El Reno tornado quite a bit, and she took these pictures, which are, if you start, this is the earliest time frame going left to right, and then down to the bottom, which is the latest one. There's only about 4 minutes apart. And so if you're just kind of scanning, this top one at A, you got some kind of lowering, maybe wall cloud B, then all of a sudden there's a little appendage, maybe a little funnel here, and now I've got a full-fledged tornado, and this is a pretty good wedge tornadoes, like you can see here. So it appears, at least visually, when we're looking at this, looks kind of top down, but is it really? And I'm not going to get a lot of the detail, but the consensus is now there is no evidence for top-down tornadogenesis. It can be a very rapid process, sometimes as little as 30 seconds, but our eyes and even the radar can deceive us with top-down, because it is most likely that tornadic rotation is probably already on the ground or very low to it. So, and as spotters, this is another good reason to really focus on the ground and not so much just keeping your head up in the clouds, so to speak. All right. And that's a lot of hand waving and stuff. I'm going to skip that one. Okay. So now back to our teaser question, where we talked about lots of tornadoes in Weld County and just east of DIA. What's going on here? Well, a lot of research has been done over the years, decades really, and there's a thing called the Denver Convergence Vorticity Zone, or DCVZ, or we like to just simply call it the Denver cyclone. And how this develops, if we follow this green arrow, we have a lot of southeasterly winds coming off our Palmer Divide to the south of Denver. And as that flow then starts to accelerate down, and then it goes up, and then as it encounters this higher terrain, the Cheyenne Ridge to our north, that acts as a blocking mechanism, turns the wind, induces low pressure over Denver, and then voila, we have this Denver convergence zone or boundary. And the way it kind of sets up, pretty much a lot of times right over Denver, just east of Denver, and then extending up to, say, DIA. And so if you live, say, from DIA down to, say, Aurora, and down further south towards Parker, that's a very familiar area for this boundary to set up. And a lot of times we get these non-supercell tornadoes that develop along the boundary. Now notice ahead of the boundary, you've got easterly, southeasterly winds. Behind it, these northwesterly winds, which are downsloping winds. Remember we talked about upslope, and that's moisture and clouds. Downsloping is the opposite. It's a drawing wind, and say you live from Boulder to Longmont or Niwot, Berthoud, and you wonder why the thunderstorms in the summer sometimes skip over you, and you look to the east and the big clouds are developing. This could be one of the reasons why. Well, with time, this whole boundary may slip off to the east and in effect those counties through Adams, Arapahoe, Morgan, and Washington counties. And again, so a lot of this, the high numbers of tornado frequency can be attributed to this Denver cyclone. Now, most of the tornadoes that we do see along these would be mostly the non-supercell or landspout weaker tornadoes, which is a good thing. Okay, this next movie I'm going to show you is an example of our Denver cyclone boundary. Just to orient yourselves, that black dot is the radar at Front Range Airport. DIA is up here, just to the northeast. And notice this, the radar is showing this boundary. Now, it's not precipitating anywhere. And actually, all it is a collection of, or convergence of bugs and insects. So the radar is really sensitive, and it can pick all that stuff up. But it's a really great tool for the meteorologist, because I can see these boundaries developing in the morning, and that is going to give me kind of a pretty good guess on where thunderstorm initiation might be on that afternoon. Now notice it can just sit there. It can become stationary like it did over DIA here. You know, they didn't consult the meteorologist before they built this airport. Okay, next slide. This is going to kind of be a pretty good example of what realistically what you might see from a landspout tornado. It's not like those big old supercell tornadoes I showed you from Mike Oblinsky's Vorticity 2 a few slides back. This, you got to do some squinting. And this, you can't just look. So if I'm looking up here at the cloud base where my upper yellow arrow is, say, oh, there's a nice little funnel cloud, and you report that in as funnel cloud. But as spotters, we want to train you guys to kind of look through the entire part of the atmosphere from that funnel cloud and cloud base all the way to the bottom, because a lot of times you're not going to be able to see the middle part because our atmosphere can be a little bit dry. You're not seeing that condensation rotation until you look at the bottom, and then you see this swirling area of dirt and debris. You put those two together, and the correct call on this would be, I've got a tornado on the ground because I see debris on the ground. So hopefully that makes sense. Now, when we talk about just plain funnel cloud, as shown in this example, you know, here's a funnel at the cloud base, but there's no complete extension all the way to the ground level. And we would just call that a funnel cloud. No big deal. Here's an example of a shot that was taken last summer from Long's Peak. And a pretty good looking dark thunderstorm rolling up in the mountains. And there's this interesting appendage right back in here. It's pretty far away. We can zoom in a little bit. But as spotters, probably your best call on this is you could say, well, that's probably a funnel cloud. I can't say tornado because it goes behind that ridge line. I really don't know how far it is behind there. And I'm going to skip to the next slide. But luckily on this day, I had another spotter from the University of Colorado, UCCS. He was over at Grand Lake, and he was looking at that same storm, and he sees this nice looking funnel cloud. But we can verify the first report of funnel and saying, no, there's no extension. And yeah, maybe I can't, I'm not 100%. We're going to call that, that's just a funnel cloud. There's no complete visible thing to the surface. And based on what we can see, there's probably nothing at the ground level either. Now our radar, for pointing it up in the mountains, it's harder to see. We could certainly see the storm that day from the reflectivity and the velocity. Maybe a weak little circulation, but not enough I'm going to get excited about and actually put out a warning on it. And here they are side by side. I point this out because even though we have spotters, they all might be looking at the same storm, but they also may be looking at different vantage points, different distances away, and each one is going to offer their unique perspective on what they can see. And that's also going to help fill those missing voids or the missing puzzle piece to our story. All right, one last circulation we want to talk about is the gustnado, or maybe better known as dust devil. These are not tornadoes, they're not funnels. These are kind of the opposite of funnels, because these guys have circulations that are rotation close to the ground, but they don't extend to the cloud base. There's a gap in there. They kind of just do their swirly, whirly thing, not following anything in line with what's going on aloft. So that's a gustnado. So here's a schematic showing our landspout and gustnado. So where would you normally see these? Well, as we've talked about already, your landspout tornado is again going to be under your updraft portion of your storm. Unlike your gust tornado or a dust devil, where again is going to be on that leading edge of your outflow from your storm. So if you're kind of got your situational awareness going, you kind of understand the storm structure, maybe where you're at in relation to the storm, you'll be able to figure out what kind of, if you're not sure, is this a gust tornado or land spout, but you say, oh, well, wait a minute, there's a shelf cloud there, and I'm in the downdraft section, so that's probably a gust tornado. If you have any questions. All right, and now here's some more time lapse, and we'll be able to see these little gust tornadoes, dust devils. Notice they're just kind of these swirling things, fall on the ground, doing their own little thing. Notice how they don't kind of stay along very long. They just kind of, just like your scud clouds, they kind of dart in and out of existence. They're not going to hang around. All right. So here's a still shot of a picture that was taken from the Virocamera network up by Alt, and this was from last March 22nd. This was 2019. And I'm going to bring a few other aspects of the clouds into view and talk about the specific site. First, notice this whole kind of deck of clouds. And essentially, it's along a kind of a boundary thing, and kind of I've outlined it here in white. And along this boundary, you can notice several little towering cumulus clouds going up. And so we're going to infer there's some updrafts here, here, and here along this boundary. Now, there's something else. If we look over here on this far left, where this red arrow is, there's another little feature. We're pretty far away. We're probably, I don't know, a good 10 miles or so away from this feature. And to hazard a guess that far away, I don't know, there's a little bit of dust getting kicked up. Maybe it's a gust tornado. Not quite sure. And so maybe that's one vantage point from a spotter. Well, I need to get a little closer view. So we call somebody up a little bit closer. This guy is east of Eaton, and he kind of sees this line, and notice this little appendage. It's behind the building. So we're still can't get beyond calling it more than just a funnel cloud. We got to get a little bit closer still. And voila, we did have confirmation of a weak landspout tornado, with this video being taken maybe only a mile away or so. So essentially, this picture here corresponds to this red arrow right in here. So along this boundary, we could have had numerous landspout weak tornadoes along this whole area here. It just so happened this was the one that was noticed. Okay, here's just a quick summary of the circulations we've already talked about to keep in mind before we get to our case study. Notice here we have our full-fledged tornado, wall cloud, supercell tornado, our funnel cloud in here. This will be an example of our gust tornado gust tornado dust devil over here on the far right, where it's got a circulation ground base, but there's no extension up to cloud base. All right, we're going to sort away from the tornadoes for just a minute so I can talk to you guys a little bit about weather radar. Radar is a great tool. It gives us a ton of information. And I want to briefly show you how it works a little bit. And in this schematic provided by Comet, if our radar is here and it sends out these little pulses of energy, hits the storm, and a portion of that energy comes back to the radar and then gets displayed on our screens. Well, it sends out a pulse of energy, and then this is all happening very quickly. The radar is scanning at low elevations, and then it rotates 360 degrees, tilts upward to the next elevation scan, and can actually go all the way up to about 19 degrees. It can do this in under about 4 minutes. So we're gathering a lot of data very quickly. And the results of that data appear in these two products. So in this upper left, this is the example of our radar reflectivity. These are all available on our website that you guys can look at. And the reflectivity is showing that power return. So the higher power of the oranges and reds is indicating heavier precipitation. The bottom right is with the greens and the reds is showing the velocity. So we can see a lot of information on storm motion and circulations, and if then maybe we have a tornadic circulation, that velocity is going to help us determine that. We can also look at radar rainfall estimates. So this is kind of a handy tool. Unfortunately, sometimes the radar doesn't do a great job. Sometimes it overestimates or underestimates. And that's why it's good to have spotters that do have rain gauges, and that way we can get some ground truth to see how good the radar is estimating rainfall. Well, as good as the radar is on doing a lot of things, it does have its limitations. And this example shows this pretty well. So, oops. Oh, there's that darn thunderstorm. I forgot to turn up the volume there. It's going to do it one more time. There we go. Now you know you have two thunderstorms, A and B. Our radar is over here at Front Range. And if we are interrogating storm A here, say we've traveled off I-76 towards Fort Morgan, and we're about maybe 5,000, that beam is hitting that storm at the low levels around 5,000 feet off the ground. And so I'm probably going to interrogate that storm and get slices through storm A, and I'm going to know pretty much everything I need to know about storm A. But now I've got a storm B that's much farther away. So if I'm driving on I-76, I'm past Sterling, and now as I'm looking at storm B, because of Earth's curvature and beam spreading, now the lowest part I can see from that storm B in Sterling is about 10,000 feet above the ground. And if I'm further yet, say I'm around Holyoke in Phillips County, I'm 16,000 feet. And so now the question is, what is going on with that storm below 16,000 feet? And the answer from me is, I don't know, you tell me. Because this is where the limitations of the radar are getting bigger as we get further and further away from the radar. And I really are relying more heavily on the spotters that are out on the roads, especially as you get out to Sterling or Akron, and those folks where my beam is overshooting the storm. And so that's kind of a critical piece of information. So ground truth, very important with these storms further away from the radar. Okay, we are going to look at our case for this evening. And I want you guys to kind of think about what we've learned so far in terms of circulations, whether it might be a tornado or a funnel or just a gustnado. I'm going to first show you a piece of the puzzle, and we're going to go through the video presentation. This actually video was shot down in Texas, but could easily have been something here in Colorado. And I'll tell you right now, it's not clear cut, and it's not a big, one of those easy supercell pick'em tornadoes. So this video runs just under 2 minutes. And so kind of put on your thinking caps, think in the back of your mind what might be going on, and then we'll give you another piece of the puzzle. So go ahead, and I'm going to click this. Go ahead and watch. Think what you see is, as a spotter, how would you call this? It's interesting. You can see a little bit of extra stuff getting kicked off, and he is zooming in there. Okay, and so that's the end of the video. So kind of think in your mind, after watching that, what you like to call it, and kind of keep that slotted back there, and we'll give you another piece of the puzzle. Okay, now we're going to add a little bit of radar to the information data set that you're collecting. So from this, on the right panel, this is the Amarillo radar. In the gray, the area of note. Notice this kind of linear green-blue area. There is a little bit of a stalled outflow or front along here. There's no precipitation falling on this yet. And over here on the right is our velocity. And notice these little couplets or little shear things. Here's one here, 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 and down here. And I'll circle these. Okay. So there's another piece of information. All right. And then based on what you were thinking of before, adding the radar, would that change your mind at all or not? So again, you could guess funnel cloud, gustnado, landspout, or not sure, insufficient information given. So just kind of think about that. All right. And now based on all the information I've given you, and now I'm going to, what we've done is we've talked to a number of sources, even our own Paul Schlatter, who's a big radar guru. He's our science officer here in the office, a bunch with other folks. From polling all these guys, here was the answer that they came up with, that this is a landspout or weak tornado, based on the following reasoning. The radar shows a great shear signature, couplet along the boundary. The ground and cloud base appear to be rotating together. When I first saw this video, that's what I kind of latched onto, that both circulations were rotating together. There was also, they noted, turbulent rotation at cloud base, but the one deferring comment was they couldn't make a distinction landspout because they couldn't see if there was any towering cumulus above the boundary. And with the information given, we're just not sure. The video is focused in enough where we can't see what might be going on above that cloud level. So you may or may not agree with the consensus, but hopefully adding pieces of the puzzle made it a little bit easier. One thing you might see us issue, maybe not a tornado warning, but if we're dealing with these landspout, if we have a boundary out there, maybe we don't have any reports yet, you may see us issue what we call a special weather statement, and in the headline talk about brief landspout tornadoes possible. And so we may do this on occasion. This was an example from last June 16th, where we had a boundary over DIA, and we even mentioned about landspout tornadoes in or close to Denver International Airport. So you may see us do that instead of maybe even issuing a tornado warning, because maybe our confidence level is not high enough, we don't have any reports yet, or they're just kind of too weak to really even see on the radar. A couple things to consider. Always, again, safety first, by if you're videotaping or taking pictures, doing it from safe distances, and also to zoom out once in a while. So unlike the example here on the left, where you're just seeing the close in part of the ground feature, zoom out like that photo that we were looking at from the alt landspout, where you might be able to see, ooh, this is on a boundary, ooh, there's under a towering cumulus cloud. And if indeed we were looking at something under this, one of these towers, that might help us decide we're looking at maybe a landspout. And then kind of in summary, when we're looking to say, is this a tornado or not? Again, always look at the full vertical structure. So from ground to cloud base. Do I have an intense circulation on the ground? Does the circulation at the surface appear to be connected to cloud base? And another helpful way is, are there towering cumulus clouds above the circulation? That would indicate updraft. So kind of keep those in mind when you're out in the field thinking about, okay, what am I really looking at? Okay, so now we're going to move away from tornadoes for a bit, and I want to just talk to you about a few of the products that will help you on your situational awareness as you go through your daily routine. And we'll start here on this slide with this inverted pyramid. And on the top of our pyramid is kind of our what we call outlook. So we're kind of days in advance. So maybe we're 2 to 3 days out. And this is all in our what we call the SPC focus. And SPC stands for the Storm Prediction Center, and they're out of Norman, Oklahoma. And they're looking at the kind of the big scale picture, looking nationally. Where nationally is my focus for the biggest, the baddest storms on any given day? So they're the ones doing the outlooks, doing the discussions. They're also the ones that are going to issue the severe and tornado watches that you guys see come out. Usually those are put out well in advance, and they may cover for maybe a 5-6 hour period. They will also call us. So there's always coordination between SPC and the local forecast office. Hey, do you guys think we need to issue a watch? Does the environment, is it conducive enough to produce severe weather and or tornadoes? And we can say yes, and we'll go for a watch, or no, let's not do a watch quite yet. And then finally, the forecast office, our office, will be the ones issuing that tornado warning or severe thunderstorm warning. This is an example of a map you might see from Storm Prediction Center. This is the example of your day one outlook. This is an example from last August. And most of the time, when we're dealing with severe, we're going to either be in this dark green or the marginal isolated severe storm, or the yellow, or we have maybe scattered severe storms. And notice in this example, once in maybe a handful of times, a couple times during the summer, somewhere in Colorado, we might be under the enhanced or the orange portion. Guarantee if we're under the orange, someone's going to get severe weather in Colorado. And luckily, the reds and the purples are for the big EF4, EF5 days, and we're not going to worry about those. Okay, so those are the day outlooks from SPC. From our office, a couple products you might want to look at is our weather story. And if we're on our homepage at weather.gov, on the bottom left is usually a picture. And it will give you kind of a visual of what's the biggest impact to be expected over the next, say, 12 to 24 hours. Well, in this example, it's still winter and it's blizzardy. So it's blizzard snow. But in the summertime, we're going to be putting on there things like, is this going to be a big impact of hail day, or is this a tornado day? Going along with this weather story is going to be your text product. This is your hazardous weather outlook. And you could click that just to the right, bottom right of this point and click map over here. And it'll give you a little bit more detail on what to expect. Plus, at the bottom, notice here, there's a spotter information statement. And this will let you know if spotter activation is needed or maybe anticipated on this given day. So that's our HWO. So again, with our watches issued by the Storm Prediction Center, conditions are becoming favorable for severe weather. Could be multiple counties, a pretty good chunk of real estate. And again, the warning meaning conditions are either imminent or already occurring. Usually warnings are going to be issued for a much smaller area, maybe 1 or 2 counties, and time will be usually 30 to 40, 45 minutes for our length of warnings. And here's just kind of a graphic of showing the aerial extent of a watch versus warning. Notice in the yellow area indicates the watch covering a pretty good area of real estate versus the much smaller warning polygon noted here and say just covering a few cities. The idea is we don't want to overwarn folks that aren't really in harm's way. The types of warnings we can issue with thunderstorms is either tornado, severe thunderstorm, and the definition for severe is at least 58-mile-per-hour wind gusts or large hail equal to or greater than 1 inch in diameter. You can also issue flash flood warnings. When you guys are reporting hail, besides the average depth and size, always give us the largest hailstone. Measuring with a ruler or tape measure is best. You can also, if you don't have a ruler with you, compare it to a coin or a ball. Notice that a quarter is about the size of 1 inch diameter. So it's kind of a handy information to know. And if your hailstone measures 4.8 inches or greater, that could be a new record hailstone. We did have a record last summer, which I'll mention here in a minute. But notice for measuring hail, this is a great way where you can line up your hailstone with your tape measure or ruler. So that's good. The picture on the right, maybe not so good. Everybody's hand is a little bit different size. Yeah, it's not really telling me much, but it's fairly big. At least probably golf balls. And then you can compare hailstones to different objects, common objects. So again, anything 1 inch or greater, like average 1.5 is ping pongs, 2.5 tennis balls, and God forbid the 4.5 softball size hail. We always get a question of, or we'll have folks still call us in with, I got marble size hail. Well, if you look at this picture, not all marbles are the same. So we asked, don't call in with marble size hail, just too much of a difference. And then we have plowable hail. So we've been working over the last few years with the University of Colorado with a joint study on learning more about plowable hail, meaning I've got a lot of small, maybe pea-size hail, but they're 6 to 8 inches deep, and they're creating some impact because I got to bring out the snow plows. So if you're seeing that kind of a situation, like you see in this picture down by the pinery, call us in, plowable hail. When we talked about big hail, we had some doozies last summer, August 12th. Big day, severe day. We had 5 confirmed tornadoes in Washington County, along with very large hail, probably a little bit bigger than 4-inch diameter hail in Otis. So you can see this hailstone here in Otis and some of the big damage to some of the vehicles that it had done. And this same day, this was also still, we're here northeast of Otis with the same storm. It also created a tornado with it. And from our spotter, you can see indication, notice, remember those bright white clouds? That's that RFD we were talking about. Excuse me. Wrong way. Here we go. Then lastly, one day later, another big hail day on August 13th. This was the Storm Prediction Center Day 1 outlook. Remember how I said we should be a little bit worried when we're in the orange? Well, that was a good day to worry because this was the day we had record hail in Bethune, Colorado, where the state climatologist went out there and the measured diameter of 4.83 inches. So that broke our new record. The old record was 4.5. We had numerous reports of 4.5. and now our new record is 4.8. So kind of a big deal there. Finally, wrapping things up, it might be good, just kind of go through a daily checklist. Kind of, again, hopefully for your situational awareness, where you get up, first score priorities, get your coffee and donuts, right? Check the latest forecasts at weather.gov. Look at the weather story, hazardous weather outlook. Take a look at that spotter activation statement. Are spotters going to be needed this day? Check SPC, that day one outlook. Are we under the threat for severe weather? Are we under either the marginal or the slight or the enhanced risk? What kind of a day is it? Is it going to be a tornado day, a hail day, or a flood day? And then during the day, kind of keep an eye on your cell phone. Any watches or warnings that might be issued by either SPC or our office. Keeping your cell phone charged. Keeping current with the local radar and apps. And if it is a tornado day, just stay off the road. Be safe. All right. Well, guess what, guys? We are coming to the end of this presentation. Just a couple of notes. So once I get all the information in, for new spotters that you've never been trained before, you will get a spotter letter and a number sent through the email based on the registration I get from you folks. And I'll also be giving you some PDF handouts, which has all our phone numbers, websites, all those things you might need, guidelines on when to call in for severe weather. Probably give me a week or so to get all this processed. If you've already got a spotter number and have already been trained, I will update your information in our spotter database, but I won't send you any formal re-notification. And maybe you have already forgotten your spotter number. That's easy. Just send me a quick email and I can look that up for you in our database. If you guys have further comments or questions on the training, again, you can contact me. I am, again, scott.entrekin@noaa.gov. Our warning coordination meteorologist is Gregory Hansen, and he's the big guy in charge of the program. So either of us, you can have further questions. So that concludes my presentation, and I'll be here if we need to answer more questions. I'll go back and look at the chat, and also I'll hang out here for a few more minutes. But again, thank you guys for your attention. Hope everybody is well during these weird times. Stay healthy this summer, and hopefully next year we'll be able to see each other in person. So thank you very much.